Welcome guys. This is the second video on day 2. We're talking about chapter 3, the normal distribution. We're going to split this up into 2 parts. The first half is going to be today. The second half is going to be tomorrow when we talk also about correlation. That's going to be a really cool lecture, and we're going to look at relationships there. But today we want to talk about the normal distribution. This is a very important topic for the entire course. We're going to be using the normal distribution throughout this summer term. So we've definitely got to get familiar with it. We're going to be doing a lot of examples. We're going to be thinking about the mean and standard deviation as it relies to the normal distribution. And we're also going to be thinking about something called the 68, 95, 99.7 rule. That's going to be a really good way to get a sense of where the data are located in relationship to the mean. Yesterday, we talked about numerical descriptions of a data set, and 2 really important ones were the mean and the standard deviation. Remember, the mean gives you a sense of center. Standard deviation gives you a sense of spread. So we want to get a sense of how far the data are spread from the mean. All right, let's get into it. So we're going to be doing our PDF notes as normal. We're going to be looking at an example with Wayne Gretzky today and look how incredible he was and why he is the great one. So let's get started. All right, we'll go full screen and let's talk about the normal distribution. I wanted to start off with an example to give you a sense of what the normal distribution is. So it gives us a sense of how the values that a variable can take on are spread. So the variable of interest is going to be height of students at Roanoke College. So I've got the height of all 2,000 Roanoke College students, and I made a histogram in blue. Okay, so you can see that 68 inches is the mean. All right, I'll tell you a little bit more about this notation in a little bit, but there is the mean, 68 inches. It's the center. And then standard deviation, I'm going to call sigma when I talk about the normal distribution, but these correspond to X bar and S from yesterday's lesson. Now, what are they telling us? They're giving us a sense of the center, 68, and the spread, 4 inches. Now, 68 inches corresponds to 5 feet, 8 inches tall. Now, what you can see here, 80, which is 3 standard deviations above the mean, that would be 6'8". You've seen some basketball players walking around campus 6'8", but there are very few that are 6 feet 8 inches tall or taller. The same is going to go down here at 4 feet 8 inches tall. There are very few students on campus that are below 4 feet 8 inches tall. So one of the key things that we want to do today is think about a density curve. This beautiful red curve is my density curve. And remember, we've talked about this. It gives the overall shape of the data. So we've got that histogram in the background, and I'm thinking about the overall shape or pattern, and I am using this density curve to explain it. So the normal distribution is how I can describe this distribution of data. I would say that these data have an approximately normal distribution. Some key words that I'm going to use are mound-shaped and symmetric. Symmetric about the mean, 68 inches. So there is an example of a variable, the height of Roanoke College students, that has an approximately normal distribution. And we're going to be able to calculate a lot of information about the heights of Roanoke College students based on this normal distribution. So for example, looking ahead, I could say, this is a question I'm going to answer. 95% of students are between what 2 heights? Are between blank inches and blank inches. All right, let's move forward. A density curve, the one that I showed you on the last page was a normal density curve, but a density curve does not have to have that mound-shaped and symmetric distribution, but it does have to have the following 2 properties. It has to always be on or above the horizontal axis, and it has to have exactly one area underneath it. So let's look at a normal density curve. I'm just going to draw really quick. It looks something like that. All right, here is the mean. I'll tell you more about that and why I'm not using X bar. But for now, let's just think about the area underneath it being 1. So if the whole area underneath it is 1, then what is the area to the left of the mean? So what percent is less than the mean? A visual inspection is going to tell us that the answer to that is 50%, right? Because the whole area would be 100%. So the proportion would be 0.5. And that's for a symmetric distribution. We're going to be able to get a sense of what percent or proportion of a population takes on certain characteristics based on these density curves. And it says it gives an overall pattern of a distribution. So I want to examine the next box, considering 2 different density curves. All right, let's see. Let's get a red one. And this is going to be skewed. All right. I say that that density curve is skewed, as opposed to this density curve that is symmetric. Now the total area under each of these curves is 1. Notice they're always on or above the horizontal axis. So let's think about 2 measures of center from yesterday's class, the mean and the median. If you were to put your finger on, let's do this one first, and balance it, you would do that right in the middle. And what that is the balance point. You could balance that right on your finger. It also corresponds to the point that splits the total area under the curve in half. Okay, so that is different than the median over here. All right, on this one, this is the mean. The reason that it is to the right of the median is the idea here, these values are far from the mean. So if you were balancing that curve on your finger, the fact that that was far from the center would make it balance on your finger here, even though this corresponds to 50% of the area is here and 50% of the area is here. That is the median. Okay, so the mean takes into account how far the values that the variable takes are from the mean, and the median is simply going to be the point that splits it in half. I hope that that is clear for you. So to review, density curve, always on or above the horizontal axis. They can take many different shapes. You see the red one is skewed to the right. You see that the blue one is mound-shaped and symmetric and has an approximately normal distribution. We'll talk more about that in a little bit. The mean and median are 2 ways to measure the center, and they each have their own properties that we just discussed. Let's keep moving forward. Oh, okay, so normal curves have the same overall shape, symmetric, single peak, bell shape. And specific normal curves are described by the mean and standard deviation. So let's say that a variable x had a normal distribution, mean mu, standard deviation, sigma. Now these are parameters. They describe the overall population, and they're 2 numbers that are going to describe the overall shape. So for the height example, if x equals height, we said that mu was equal to 68 and the standard deviation was 4. That is, I could write height has a normal distribution with mean 68 and standard deviation 4. And then I could draw that. mound-shaped and symmetric, and there is the mean right in the middle. The spread is given by this information of 4. So what I want to do now is think about how the mean and standard deviation affect a normal curve. So let me draw 2 curves. One here is a normal curve. Now my goal when I draw this second one is going to be that it's the exact same shape, it's just shifted down. So here for the red one, whoops, the mean is 10, and let's say the standard deviation is 1. Now for the blue curve, I want the standard deviation, that spread from the mean, to be the same. What's different is the mean. So here the mean could be 6, and the standard deviation again is 1. So what I'm hoping you're seeing is that as the mean changes, we have shifted from 10 on the right to 6 on the left. Now I want to think about what happens as the mean stays the same and the standard deviation switches. So let's say that this is a density curve with mean 10 and standard deviation 1. Actually, scratch that. Let's make it 2. Now I'm going to draw a green curve, and it's going to have a smaller standard deviation. Okay, there we go. Now really this keeps on going forever and ever and gets closer and closer. It just never quite touches. So this green one, now the center is the same. The mean is 10, but the standard deviation is smaller. It's only 1. Now I want you to ask yourself, why is that green curve so much taller than the blue curve? The answer has to do with the standard deviation. Remember one of the key components of a density curve. What is the total area under the curve? 1. Total area is 1. So what that is going to tell us is that if the standard deviation is lower and there's less spread, it's got to be taller, so the total area is again 1. So as the standard deviation changes and the standard deviation gets from, say, large to smaller, the width, the spread, gets narrower. Does that make sense? Okay, so you can see that as I was trying to comment right here. The standard deviation sigma controls the spread of a normal curve. Okay, so we've got a sense of some notation, how we write that a variable has a normal distribution. We have an idea of what the mean does as it changes and the standard deviation. So now let's think one really useful thing about curves like this. Well, before we do that, I've got this definition from the book, and it's what we were just talking about. I just wanted to get it out here. So it says a normal distribution is described by a normal density curve. And there are 2 numbers that specify the exact distribution, the mean and the standard deviation. These are parameters, and they are numbers. Okay. This, I think, is one of the most important things that we're going to be talking about today. This is called the 68, 95, 99.7 rule. Another name for it is the empirical rule. Whoops, I misspelled that. Empirical rule. It's just another name for it. The 68, 95, 99.7 is a great way to describe it. So do you remember that question that I asked that said, whoops, wrong thing. I said 95% of students are between what height? blank inches and blank inches. So the way that I'm going to answer this question is using the 68, 95, 99.7 rule. Now specifically, I'm going to use this right here. It states approximately 95% of students are within 2 standard deviations of the mean. All right, so let's go to our example with students. And I would like you to remember that X, the height of students, has an approximately normal distribution with mean 68, standard deviation 4. So the mean is 68, standard deviation is 4. Okay, so 2 standard deviations above the mean is going to be 68 plus 2 times 4, which is going to be, let's see, 76. So 2 standard deviations below the mean is going to be 68 minus 2 times 4, which is equal to 60. So I now have used the 68, 95, 99.7 rule to answer my question. So 95% of students are between 60 inches and 76 inches. Not too bad at all, okay? Note 60 is 2 standard deviations below the mean. 76 is 2 standard deviations above the mean, and that is exactly what we used right here. 95% fall within 2 standard deviations of the mean. Okay, so let's get a new page. I'm going to insert a page. Okay, and let's do another example. But before I do this, I did not mention a key thing. The distribution must be normal, approximately normal, or at least mound-shaped and symmetric. That is important for this rule. All right, so let's go on to the next page. LeBron. Okay, so let's let X equals points per game LeBron scores. Okay, so X is the points LeBron scores. Let's talk about his distribution. Well, of points, it's approximately normal with mean 26, standard deviation, let's do 3. Well, I'm going to take that back. This is not exactly correct, but let's just use it. 5 is going to be his standard deviation. So if I made a picture of this, and I had my mean of 26, and then I want to move out 1, 2, 3 standard deviations above and below. Notice I'm just going to add a standard deviation here, 31, this plus 2 standard deviations, 36, plus 3 standard deviations is 41, and below we can do the same thing. I don't think it's going to be too big of a mystery how I'm doing this. So let's think about what the empirical rule would say about him scoring between 31 and 68. In terms of the area under the curve, this is approximately 68% of the area is between 21 and 31. So this is going to tell us LeBron between, let's see, 21 and 31 points and 68% of games. Now, forgive me for this statement here, where I said LeBron's points have an approximately normal distribution with mean 26 standard deviation 5. That's not exactly true, but I just wanted to give you an example that you were familiar with. The distribution is not normal, but we're assuming it is, and we can use it to do this calculation where we say between 21 and 31% of, I'm sorry, between, let me start over there. In 68% of his games, he scores between 21 and 31 points using the empirical rule. Okay, so let's do another example. I really like this rule, and I want to tell you a little bit more about it. So I'm going to add another page. And let's do one with IQ. IQ example. So let X be a person's IQ score. Now this is one measure for intelligence. It's not perfect, but it's going to be good for our example. So IQ in the United States has an approximately normal distribution with mean 100 and standard deviation 10. So I can very easily draw a relative frequency diagram for the normal distribution here. Whenever I do this, I like to label the mean and then go out 1, 2, and 3 standard deviations in each direction. Notice 120 is 2 standard deviations above the mean, 130 is 3 standard deviations above the mean. It shouldn't surprise you that I am marking out 1, 2, and 3 standard deviations in both directions. Okay, so let's ask a question like, what percent have an IQ over, say, 120? All right, so the first thing I'm going to note (120) is 2 standard deviations above the mean. All right, let's mark this here. So I want to know what this shaded area is. What proportion of people, which corresponds to that shaded area, have IQs over 120? All right, well, let me start by answering a different question. Okay, so I want to know about 2 standard deviations. Let me get a different color. I want to know about, in general, 2 standard deviations from the mean. So we know that 95% of people have IQs between 80 and 120. Why? What does 80 represent? Well, it's 2 standard deviations below the mean. The mean is 100, and then 2 standard deviations. Standard deviation is 10. So 95% have an IQ between 80 and 120. Okay, perfect. So let's just use kind of some logic. If 95 have between 80 and 120, then 5% below 80 or above 120. So that's just 100% minus the 95 between. Symmetry, since it's symmetric, we know that half of that 5% are here and the other half are here. Symmetry tells us that 2.5%, half of the 5% not between 80 and 120, are above 120. All right, so we could do that for any, I could say something like, well, what percent are above 110? I could do what percent are below 90. I could do what percent are between 80 and 110. And I think that you could use this, idea of geometry to answer any of those questions. All right, that is the 68, 95, 99.7 rule. It works for distributions that are normally distributed or, mound-shaped and symmetric approximately. And it's just a great rule of thumb for getting a sense of how much data are between certain values. And one of the keys here was we were thinking about being between 1, 2, and 3 standard deviations from the mean. This picture here, I really like. It shows you this idea of 68% of the area or data are within 1 standard deviation, 95 within 2, and 99.7 within 3. We looked at height. Whoops, wrong way. We looked at this. Well, where am I going? Oh, we looked at this height example to do the empirical rule. We looked at LeBron's scoring within 1 standard deviation, and then we kind of got a little creative and said, well, how many are more than 2 standard deviations from the mean? Okay, so we talked a lot about the number of standard deviations from the mean, and I want to tell you about standardizing and z-scores. This is a really important idea. It lets us think about relative standing, where an observation is in relation to the mean, okay? So let me see here. Let me get out of this. Let me pause it. Okay, so I want to think about z-score and relative standing. And to do this, I want to do an example with hockey. NHL playoffs are going on right now. And we've got Sidney Crosby, a great Canadian, and it's making me think about Wayne Gretzky. So let's do an example with Wayne Gretzky. I pulled some data about NHL leading scorers, and I found that on average, we had 48 goals it took to lead the league in scoring, with a standard deviation of 17. So on average, to lead the league in scoring, you need to score 48 goals with a standard deviation of 17. Now, one particular value, Gretzky, scored a record 92 goals in a single season. That is an extraordinary. Notice how far it is from the mean. Now, what this z-score lets us do is it lets us calculate the number of standard deviations an observation is from the mean. That gives us a good idea of relative standing. So let's calculate Wayne Gretzky's z-score. So you notice that z is the data point minus the mean over the standard deviation. So for Gretzky, z is equal to 92 minus 48 over 17, which is equal to 2.58. All right. He was 2.58 above the mean. That is incredible. He was far, far, far above the average. Whenever you start to get into more than, say, 3 standard deviations from the mean, this is truly extraordinary, right? That would be about 1 in 1,000 would be 3 standard deviations. Let's think about another z-score, and let's think about it for Mensa. All right, so z-score, again, it's measuring the number of standard deviations from the mean. Let me write that down. All right, so he was 2.58 standard deviations above the mean. Let's think about Mensa. Mensa is a self-described group for geniuses, and they let you get in based on your IQ. So Mensa says if you get an IQ test score of, let's see, I've got a lot of different ones I'm looking at it, but let's just do about 130. So entry for IQ 130 or above. Whoops. My computer was a little slow there. Let me just do this again. Above. All right, so what we said was X has a distribution that is normal with mean 100, standard deviation 10. So we note the z-score for entry of 130 is 130 minus the mean of 100 divided by 10, which is 3 standard deviations above the mean. Okay, so that is pretty extraordinary. You notice that that is far, 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 far above the mean. 3 standard deviations corresponds to roughly about a 1 in 1,000. So about 1 in 1,000 people could qualify for Mensa based on this process. Let's also think about z-scores can take on negative values. Let's do another example. All right. So let's do, let's see, let x equal hours of sleep. And let's say at Roanoke College that this has an approximately normal distribution with mean 7 and standard deviation, I'm going to say 1. All right. Okay, so we've all been there. You were cramming for exam night. Billy only got 1 hour. So this 1 hour, let's find the z-score. Let's find this z-score. Okay, so the z-score is going to be the amount of hours that Billy got, which was 1, minus the mean, 7, divided by the standard deviation, 1. So this is a -6. This was very unusual. What I'm hoping is that it's very rare that a Roanoke College student would sleep 1 hour per night. We've got to get more sleep than that. So this is going to correspond to 6 standard deviations below the mean. Okay, does that make sense? Oh, and I forgot to mention this, but we gotta have a special number for chapter 3. You're gonna look on the homework for this, and the special number for today's lecture is 142. The special number is 142. So today we talked about the normal distribution. All right, remember. We describe it using a density curve, and whenever you see this density curve, I want you to think about kind of a histogram underneath it because you have a good intuition about what information is contained in a histogram. There are 2 parameters associated with a normal distribution. These are numbers that describe the shape. One is the mean that describes the center. It's and so this is a Greek symbol. Sorry, I didn't mention this, called mu. And this is a Greek symbol called sigma, and it measures the spread for. Now that you know about the 68, 95, 99.7 rule, does it surprise you that on this are marked 1, 2, and 3 standard deviations above below the mean? So going back to the z-score, we see here, if you are 60 inches tall, your z-score is going to be 2 standard deviations below the mean, so that would be -2. If your height is 72, your z-score is going to be 1 standard deviation above the mean. So that's what we did for z-score. We used the empirical ruler, the 68, 95, 99.7 to calculate different proportions. And I hope you've got a good sense of the normal distribution. Tomorrow we're going to come back and calculate exact probabilities, but I hope you have a great night. Good luck on the homework, and we will see you tomorrow for some more statistics.